Welcome! In this lesson, we're going to be combining vertical and horizontal translations into one graph, right? So we're going to both translate vertically and horizontally the parent graph, y equals x squared. So a little reminder, when we subtract or add to x, we're going to move horizontally. So if it's subtraction, we know that's really x minus a positive c, right? Because the negative is already in the equation. So that's going to move the graph to the right. If we see addition, that's really x minus a negative c, and that's going to move the graph to the left. Sorry, I'm tangled on my microphone cord. All right, so now if we subtract or add to y, right, that's going to be a vertical translation. And if we're subtracting, right, we're going to move our function down. All right, so if we have minus some value, that's going to move it down that amount. If we add to the whole function, if we're adding something positive, it's going to move our function up. Right? So we can have a function that's transformed or translated both vertically and horizontally, and that's what we're going to do on this graph here. So we're going to use translations to be able to graph it. Right? So rather than finding the vertex, we're going to find the vertex, but we're going to find the vertex just by translating our function. So instead of identifying the vertex from the equation, because we could identify from the equation. So it'll be a way that you can check, right? Because you should be able to identify the vertex from the equation. And instead of plugging in 0 to find the y-intercept, and instead of setting the equation equal to 0 and finding the x-intercepts, we're going to graph this one another way. Right? Now, graphing the way we first learned it, that's an excellent way to graph it, but I want to give you some extra tools. So now this is going to be another tool in your toolbox. You're going to be able to also graph using transformations of a parent graph. All right, so first of all, let's graph our parent graph. And I'm not going to write down the table of values this time because we've written it down twice. All right, so we have the point 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, and 3, 9, and negative 3, 9. All right, so it's the same graph we've done now twice. This will be the third time. And we'll do it a lot more because this is our parent graph that we're translating. And I wonder if I can move that down. There we go. I just missed that point. So this is y equals x squared. Now let's go through our translations. Right? So let's do the horizontal first. We see x minus a value. And we know when we see x minus, that's really, we're adding in a positive value. So we have a horizontal translation, right? And that horizontal translation is 4 to the right because we have x minus a value. So we are going to shift our graph 4 to the right. Shift the graph 4 to the right. We also have a vertical translation. Right? We see something subtracted from our function. Right? So the x minus 4, that's a horizontal translation because it's inside the parentheses. So that's shifting 4 to the right. The minus 3 at the end of the function is moving the whole function, and it's moving it down 3. So we have a vertical translation. We're going to shift the graph 3 down. Okay, it's going to change the vertex. If we shift it we'll write the vertex down, and we'll also be able to check it as we translate our graph. But if we're shifting 4 to the right, that's going to change the vertex. We're going to have 4 as the x-coordinate. If we're shifting it 3 down, that means we're going to have -3 as the y-coordinate of the vertex. So now let's graph our graph here. I think I'll use red. All right, so I'm going to move every point 4 to the right and 3 down. All right, so 1, 2, 3, 4, and 1, 2, 3. All right, so let's move to the next point. 1, 2, 3, 4, and down 1, 2, 3. And then I'm going to move to the next point. All right, so 1, 2, 3, 4, and down 1, 2, 3. All right, so now let's move 2 more points. 1, 2, 3, 4, and 1, 2, 3. And so notice it has the exact same shape, right? Because we haven't dilated this at all, right? There's no coefficient in front of the parentheses there. All we've done is shift the graph. So 1, 2, 3, 4, 1, 2, 3. And the last 2 points. 1, 2, 3, 4, 1, 2, 3. And 1, 2, 3, 4, 1, 2, 3. And there we go. And we can see our shape. And after a while, you can use that fact that it's got that shape to graph even a little faster. I just missed that 1 point. I guess that's good enough. I don't know. Maybe I'll graph it one more time. Whoops. I just moved the point. I'm going to graph that. I'm going to try. I'm going to graph it one more time because my graph looks a little crooked. All right, so sometimes it's hard because I'm not, I'm graphing with my hand in the air, right? My surface is vertical. There we go, that looks a little bit better. And so now notice that the graph has moved both horizontally and vertically. This is the graph of, and I can put y equals, but since it's labeled f of x, let's label it f of x. So f of x equals x minus 4 squared plus 3. Right, that's the graph we wanted to graph. In this case, our x-intercepts, by the way, wouldn't have been very pretty. They're not integers, they are irrational numbers, right? But in this case, we didn't use them, right? Because we could just translate our graph. The domain, of course, is going to be the same all the time for our quadratic functions, -infinity to infinity. The range, the graph has been shifted. Whoops. I put the graph in the right spot, but when I was writing the equation, I accidentally put a +3 instead of a -3 there. So and I'm going to label the vertex too. So I'll move this down a bit. And the vertex is at the point for -3. Since the graph is shifted down 3, the range only has changed, and the range will be -3 to infinity. Notice we use a bracket because that value -3 is included. And there we go. Right? And you could graph this much faster than 8 minutes, but we were talking about this function the whole time, so it takes us a little longer. But that's all the steps to being able to graph using translations. Let's take a look at this graph. It's already graphed for us. We're just going to talk about this graph. And then we're also going to find the solutions, a little practice there, and we're going to talk about when a graph of a quadratic function has no x-intercepts. This is in your notes, and I'm going to have you write this part and this part down. If there's anything else, I'll write that down as well. So use the graph of f of x equals x squared as a guide, describe the transformations, and then graph the function. Right? So so you have to kind of pretend the graph's not there. So if we were actually doing this instead of having it on the board already, right? First we would identify the transformations and then we would graph, right? So let's take a look at this equation. So g of x equals x minus 2 squared plus 4. Right? We see the minus, so that means x minus a positive 2. So that means the graph is going to shift 2 to the right. So because h equals 2, right, because we have x minus, and the minus is in the equation, plus 2, the graph is translated 2 units to the right. Because k is 4, we're adding 4 to the whole function, the graph is translated 4 units up. Right? So therefore, our equation, g of x equals x minus 2 squared plus 4, is just our parent graph, y equals x squared, translated 2 units to the right and 4 units up. So every point on our graph, so here we have the point 0, 0. If we move 2 to the right and 4 up, we have the point 2, 4. Right? And that's going to be true for all of the points. We don't have a whole lot, there's not a whole lot of points that are really easy to figure out what they are. I can figure out this point, I think. I think that point is negative 2, 4. It would shift 2 to the right, so 1, 2, and then up 4. 1, 2, 3, 4, and you can see it has. So negative 2, 4 becomes 0, 8. Right? So every point is shifted 2 to the right and 4 up. Now let's talk about findings of the solutions here. All right, so if we weren't solving graphing this using translations, we were just finding the x-intercept, y-intercept, and vertex. Let's see what happens when we go to find the x-intercepts. Right, so when we find the x-intercepts, we set the equation equal to 0. So 0 equals x minus 2 squared plus 4. And we want to isolate the something squared. So we would subtract 4 from both sides. So negative 4 equals x minus 2 squared. And then we would take a square root of both sides. So don't forget over here, for the constant, we would take plus or minus. Right, so the square root of negative 4 is plus or minus 2i. Square root of x minus 2 is x minus 2, and then we'll add 2 to both sides. So our solution here is x equals 2 plus or minus 2i. Now that is a complex solution. And when our equation has a complex solution, it is not going to have any x-intercepts. So now if we look at that red graph, which is the graph of x minus 2 squared plus 4, we can see that red graph does not cross the x-axis. Right? And that's because it has complex solutions. So now what's it going to look like when our graph has no x-intercepts? Right? So we're going to have one of 2 different scenarios here. And I'm going to switch colors so it sort of stands out. So a graph has no x-intercepts when, first possibility, the vertex is above the x-axis and the graph is concave up. That's the first possibility. Or number 2, the vertex is below the x-axis. I should have made sure I oriented the board. I don't know, over here in the corner, it's just making everything go way down. Right, so the vertex is below the x-axis. I'll try to compensate by writing higher. And the graph is concave down. Okay, so one of these 2 things is going to happen. In this case, our vertex is above the x-axis. It's at 2, 4. And our graph is concave up. Right? In either situation, you will have complex solutions. All right? So in other words, when we have a complex solution, if we were to find the discriminant, although you can't find the discriminant when it's not in standard form, but the discriminant would be less than 0, if we could find it. We could if we change it from vertex form to standard form, but there's really no reason to do that. Right? We can solve it pretty easily and see that we have complex solutions. And I think, oh, no, I want to do one more. So I'm going to do one more in this video, and then I'll stop. All right, so we use the graph of f of x equals x squared as a guide. All right, we're going to describe all of our translations, and then we're going to graph. So we're graphing g of x equals x plus 2 squared minus 4. All right, so when we see a plus, we know that what we really have, I'll write in red, not green. We really have g of x equals x minus a negative 2 squared. All right, so that part there is the horizontal translation. So that means the graph is going to translate or shift 2 units left. What we add to the whole function is our vertical translation. Right? So we see a minus 3. So that means we're going to shift the graph 3 units down. It's the second one I have down. That means the vertex, if we're shifting 2 units to the left, the vertex, the x-coordinate will be negative 2. If we're shifting 3 units down, it means the y-coordinate of the vertex will be negative 3. Let's graph the parent function, and then we'll use translations to graph the graph that we want to graph. Right? So again, I'm not going to write down the table of values because at this point I'm sure you have memorized 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9, and we'll connect the dots. Not too bad. Could be a little bit better on that right side. All right, so now we're going to translate that graph. 2 units to the left and 3 down. So that means every point just goes 2 to the left and 1, 2, 3 down. And to the left and 1, 2, 3. 2 to the left, 1, 2, 3. So you start to see a pattern the way the points are going when there is no, let me just make that nicer, when there's no dilation. All right, so 2 to the left, 1, 2, 3 down. 2 to the left, 1, 2, 3. Just missing my points. 2 to the left and 1, 2, 3. And last one, 2 to the left, 1, 2, 3. There we go. And now we'll connect. And it's just that easy. All right, so the blue graph is y equals x squared. The red graph is y equals, oh, actually, I'll write down g of x. Because it's labeled in function notation. G of x equals x plus 2 squared minus 3. The domain, of course, is negative infinity to infinity. The graph is shifted. I'll write down the vertex. So that was negative 2, negative 3. The graph is shifted 3 down, so that means the range is going to be negative 3 to infinity. And there we go. So another one graphed. Right? And that's where I want to end this video. All right, so thanks for watching. That's how you graph using translations. We're going to look in the next video at dilations and reflections. Thanks for watching. Bye for now.